Hello, everyone, and welcome to this Telit Cinterion webinar, NTN, a game changer in 5G cellular networks. I'm Amanda Flink, the head of global events here at Telit Cinterion, and I will be moderating today's event. Today, we will discuss 5G advancements, which are made possible with NTN, insights into rollouts with 3GPP release 17 and above, as well as new and existing use cases that the satellite technology is enhancing. To explain this topic today, I am pleased to be joined by two speakers. First, we've got Florian Denzen, the Director of Product Strategy at Telit Cinterion. Thanks for joining us, Florian.
Hello, everyone.
And second, we have Volker Brewer, the Head of Standardization at Telit Cinterion. Hi, Volker.
Hello.
Now, just before I hand it over to Florian to start our presentation, I would just like to remind our audience to check out the resources section for some additional information. There you can find the slide deck and some other resources about our topic today. And with that, Florian, I will hand it over to you to start our presentation.
Thank you, Amanda. So our presentation today is split in two parts. So we will first look into the context a little bit of NTN. So NTN will add another layer to cellular communication. So we have some, let's say, interesting technical aspects, but also in terms of use case, very interesting opportunities. So the first part will be a little bit the 3GPP standardization and where NTN is kind of located there. And then also a little bit look at the further ecosystem, and then like a little, outlining maybe the opportunities, the use cases, and how NTN can support IoT applications. And in the second part, Volker will look a little bit further into the NTN system and we'll outline a little bit further technical details.
Yeah, I will outline a bit how NTN became part of the 5G standard of 3GPP, how NTN is included in service provisioning for broadband services, for machine type communication, but also a bit into the flexible architectures that was included in 3GPP to cope for existing and new satellite constellations, and also then the phased approach in standardization leading towards seamless interworking in future releases. Thanks.
Thanks, Volker. Okay, then I will start with the first part, which is focusing more around the general standard and the markets. So with that, let's have a look first onto the background. Where is the origin of NTN? So it is part of 3GPP. 3GPP and the 5G activities started in 2012, and initially the focus was on three main services: eMBB, MMTC, and URLLC. And of course, the initial driver were smartphones, followed then by different applications. And starting from release 17, after in release 16, the 5G standard was accepted by the ITU, a market-driven phase began. So if we look now a little bit further into this, into the activity which was kind of in parallel, which led to NTN, we will see that there were already some discussions in release 15. In release 16, a pre-study was carried out. And then in release 17, finally, we have a standard which can be brought to the market. And this, of course, is not limited only to release 17. So there's a whole roadmap behind it in further releases, which will be outlined later by Volker. If we look into the existing standards reaching from LTE to 5G and see where this NTN standard is positioned, then what we see is there are two initial kind of focus points. We have NTN IoT, which is, as the name suggests, really centered around IoT communication, so lower data rates, while NTN NR is trying to cover a little bit more the space where we need higher throughput. And there's also, of course, NR cap, which kind of represents mid-speed. This technology may become then part of NTN later, but the initial focus is really on eMBB and the MTC communication. And what we maybe also, what's interesting here, of course, we also have ultra reliable low latency communication as one of the initial 3GPP standards. Here, of course, with satellites, due to the distance latency, of course, it's difficult to find a good correspondence in terms of performance. But if we look at the use cases, I think NTN has a chance to help to have more resilience, to support applications with an alternative link if there's a link failure. So there is some sort of overlap in the use case, I would say. So looking at the services and the topologies, as we know, like 5G started with a close interworking with LTE, which you could view as a sort of topology extension. There's also the option to deploy 5G in private network environments, have dedicated networks for industrial. And NTN kind of represents another topology option, so to say, and as outlined, starts with NTN IoT and NTN NR corresponding to these already established 5G technologies. And for NR cap, we will in the future then probably see a evolution there too. So looking a little bit from above and to understand a little bit the use cases and also the grouping, NTN IoT outlined is focused really on the lower data rate use cases and adds here nicely into the path of MTC and MMTC. While if we look on the other side of the high-speed spectrum, then here initially we will see the NTN NR, and for RedCap, we will see in the future, probably in a further release, also some options here. Looking at the use cases, so in general, what we can say is that there's a great overlap with IoT use cases, of course. So we will have, use cases which are maybe mainly driven through coverage extension, so everything which is mobile or located in remote areas, but also for, let's say, more critical use cases, demanding use cases, which need resilience, or even public services, disaster relief. NTN can play a vital role here to support networks, or if some infrastructure is not working, then that's an alternative path with NTN, and so enabling, for example, disaster relief. And of course, naturally, everything airborne can, of course, then also be nicely supported if you have an NTN network, and as already implemented with other technologies, there's a good match here. So to summarize, to look at the NTN rationale, NTN complements existing terrestrial networks. So remote or rural areas can be addressed, coverage provided when services are disrupted, and of course with having an alternative communication path, reliability and resilience can be improved. And in addition, maybe also it can play a capacity role for networks, providing also this path for maybe some offloading or having additional resources available when needed. And the basis for this, what we will now in the next part will learn further, is that it can leverage the rich 5G system. There are a lot of functionalities which really enhance satellite communication, like mobility, the network management capabilities, the flexible network architecture, which allows different deployment options, and also a gradual move into this technology, and other 5G functionalities like virtualization and network slicing really adds another level to satellite communication here. And also, of course, with this NTN communication for IoT, energy efficiency can be addressed. So in the end, it's about features, but it's also about leveraging an ecosystem which already has high volumes in devices, technology components. So it's flexible in terms of choices, but it's also very interesting in terms of cost points, since we are talking about reliable, proven, mature technology which is in high volumes. With that, I hand over to Volker, who will outline a little bit further the NTN technology.
Thank you, Florian. We are looking into the NTN technology itself. Let's first look into the satellites providing that technology. When we look into the satellites, main point we should look at first is the satellites and their orbits. The satellites circulate around the Earth in different orbits. Close to the Earth, we have the low Earth orbit in a height of 500 to 2000 kilometers, followed by the MEO orbits, and far out at approximately 36,000 kilometers, we have the geostationary satellite orbit. From this scale picture, you can already see what are the challenges here. The challenges are definitely related to latency, attenuation, just the distance you have. And when you look at geo orbit being so far out, even if the opening angle of the satellite is very small, you will cover very wide ranges. The distance to a user on Earth is shorter for LEO. However, for LEO, we need to keep in mind that the satellites are moving. With respect to a fixed point of Earth, you may see a LEO satellite, as an example, in 600 kilometers for average, 3 to 5 minutes every 12 hours. So this really indicates that in low Earth orbits, you have less latency and attenuation, but other challenges due to the high mobility on that. On the other hand, satellites in telecommunication are not that new. Also in the past, they have been used. There are already use cases there today for satellites. Satellites are often used as mobile backhaul to cover distances, especially for geostationary satellites with some very small aperture antennas there, which are used to overcome that, but they're also used for broadband or broadband to device communication. Systems already existing like Starlink or Iridium. However, the big challenge for 3GPP wants to do is to include NTN into the 3GPP 5G standard, that the NTN just becomes another provisioning layer for the 5G devices and its different services. So when we look at the 5G services overall, its overview, we're seeing at the top end the EMBB, the enhanced mobile broadband services, especially handsets or infotainment systems in car. On the lower left side, we're seeing MMTC, the massive machine type communication, and on the right side, the URLLC. These three have been the IMTU 2020 requirements by the ITU, and in the middle, filled by now by 3GPP, the 5G red cap area, what we also call the smart IoT. Now, NTN standards adds another network layer. And at the beginning, NTN NR will address the 5G EMBB area, whilst NTN IoT addresses the MMTC area. However, the area in the middle, the red cap area, will also become part of the 3GPP standardized NTN services, just in a higher release. And even so, URLLC is not part of what is standardized for NTN. It's not precluded, because due to the resilience and the reliability of NTN, you definitely can also support critical use cases, especially with respect to, for example, first responder or public safety. So all services are included. Now, what are the challenges coming from the NTN? And for the challenges, let's first start with geo. As said, geo, they are stationary, they have quite a far distance, quite wide coverage area, but the stationarity of these satellites is a plus compared to LEO, where we are far closer to the Earth. However, attenuation and latency is still high. Let's keep in mind, LEO, we are talking about 500 to 2,000 kilometers height, whilst normal terrestrial-based cells have a diameter or radius of 20 to 30 kilometers, something like that, depending on the rural area. However, for LEO satellites with normal antennas, maybe an antenna included in the headset, you will see later on, you can achieve certain throughputs of about a megabit included in that. However, for LEO, you need especially also to consider the mobility aspect. As said, LEO is really, the satellite is moving, and this leads to scenarios which are like a high-speed train. Scenarios as if you would move in a high-speed train. Even so you're static, the satellite will move, and you need to accommodate for that and support the corresponding mobility. Mobility in two aspects. One is mobility for NTN to NTN, because one satellite provides only coverage for a limited time, a LEO satellite, then the next satellite hopefully will come in and gives you coverage. On the other hand, you may enter and leave NTN and TN coverage, so you want to have mobility and service continuity between NTN and TN. A further important point we should not forget is, when thinking of geo, we also need to think of that the geo satellite may cover a whole country or even several countries. This means you always also need to be careful whether by regulatory or business rules you are allowed or you want to provide a service. So positioning is also a key element for NTN. Now, what happened in standardization throughout the releases? At first, a study was conducted in release 16. The study was really agreeing on the architecture that is supposed to be standardized. First it was chosen that the transparent architecture option will be standardized, because transparent, I will come to that term a bit later, transparent and regenerative payload means that the satellite just acts as a relay. You need to consider how you can overcome and address all the attenuation problems, all the timing problems you have, because let's keep in mind, we are talking about the standardized 5G system. And the standardized 5G system has a fine time frequency grid. So even if you now provide the service via the satellite for NTN, you still need to comply and fit that into this fine 5G time frequency grid. Based on all the pre-studies done in release 16, in release 17, the normative work started. It started for NTN NR and for NTN IoT. So first of all the necessary adaptations were made to the system, means adapting the procedures and the protocol to cope with this extra latency, do the necessary adaptations, and especially also for the lower LEO satellites, consider the intra-NTN mobility, that you have the mobility between the satellites. In release 18, definitely what was standardized in 17 was enhanced. One of the points to mention is the mobility was improved for NTN to NTN, not only for NTN NR, but also for the NTN IoT. So connected mobility was introduced between the terrestrial network and the satellite network. Here especially, there was a channel of drifting timings between TN and NTN, which needed to be considered, and this measurement-based handover needs to accommodate the corresponding measurement windows on that. Furthermore, cell reselection scenarios also for cases of discontinuous coverage for FLEO satellites were addressed, and in general, capacity and throughput improvements were included in the release 18. You see how the standard evolves from the first study in 16 to the release 18. However, this is not the end, because release 19 has just started beginning of the year. And in release 19, there are two very important aspects coming for NTN NR and NTN IoT. And this is the regenerative payload. Regenerative payload means the GNB, at least the base station, is on board of the satellite. This allows for providing new services such as broadcast for NTN NR. Furthermore, in this release 19 enhancements, also RedCap devices, as said earlier, are now included to be part of NTN NR, that also they can participate and benefit from the NTN service provisioning. For NTN IoT, also regenerative payload architecture is standardized, because this is a prerequisite for store and forward. Store and forward means, especially in IoT area, you often have delay tolerant traffic. Means traffic which has a certain delay tolerance. You do not need to deliver it directly. So you can send that data to the satellite, store it there, and once the data connects to a feeder link, you can download the data and forward it there. So for all of these, the regenerative payload, the second architecture, is important. Now that I've talked so much about transparent and regenerative payload, let's have one slide to have a short look on these two architectures, how they look like. On the top, you've seen what is called the transparent architecture, as it was standardized from release 17 in the beginning. Means that the device communicates based on 5G NR with the satellite, and the satellite is just a relay and relays these 5G NR signals to the feeder station, and the GNB, the base station, is somewhere on ground. This transparent architecture allows to include also existing satellite systems into the communication for 5G NR or 5G NTN IoT. Because the satellite is just here relay the signals you have received. However, for future satellite systems and advanced satellite systems, there's now also the regenerative payload standardized. Regenerative payload means at least the base station, at least the GNB, is embarked in the satellite. So you transfer the data from the device to the satellite, and on board of the satellite, there is a GNB. So you can store there the data, like in NTN IoT, but you can also demodulate the data and remodulate, or provide it differently back to the feeder link. For example, you could use between satellites also an optical link on a longer term. So regenerative payload is really a further important step for enhancing the services that can be provided by NTN in 3GPP context for 5G. Let's really look throughout the releases, what was done, by very simple example on that. First, in release 17, it's really what we call leveraging the access hardware. Means you have a chip which can connect via a satellite to a feeder link, and you can do a call, you have a service. In release 18, with including the NTN service continuity, imagine the scenario a ship is entering or leaving a harbor, and the call is handed over from the TN to NTN or vice versa. And then in release 19, with the regenerative payload, and looking at releases beyond that, because regenerative payload, the base station on board of the satellite, is a prerequisite, you can imagine scenarios like broadcast, or two ships directly communicating via a satellite with each other on that, also for future services to be provided. On that set, we coming to, let's say, an overview slide for grouping a bit the scenarios and the capabilities on that. On the left-hand side, you see we have the frequency range included of up to 7 gigahertz. On the right-hand side, it's the frequency range above 10 gigahertz, because for satellite communication, you have various frequency ranges. So in the lower frequency range, up to 7 gigahertz, we clearly see here communication and terminal types such as IoT devices, but also normal handhelds and handsets. For IoT devices, such as narrowband IoT or eMTC services up to, let's say, 100 kilobits seem to be reasonable and realistic from today's perspective. And this is especially suited for NB-IoT and eMTC, as said. And keep in mind here, just as a side remark, they are today both still EPC based, means connected to the 4G legacy core in case of NTN operation. And this is especially for utilities or agriculture, where we could imagine applications would be. On the other hand side, the NTN NR, also in that range, addresses for handhelds or car infotainment systems, what we call wideband services. And for wideband services, let's say a few megabits may be realistic. Really, for automotive, utilities, agriculture, all these things, that's quite thing. On the other hand side, when we look at the right side, for the high frequency areas, so frequency above 10 gigahertz, you could even have broadband services of up to 100 of megabits, because there you have wider frequency bands. Due to the fact that the attenuation is pretty high, you would require VSAT, very small aperture antenna, to overcome the attenuation, but you get far higher speeds, where we see clearly an interest from professional markets, telco, backhauls, but also for other services and service types, all requiring, let's say, what we call broadband service provisioning. So to summarize, 3GPP technology addresses really all satellite networks, all orbits, any type of band, any type of service, and any type of device. It tries to have a holistic inclusion of the NTN into the 5G 3GPP standard.
Thank you, Volker. So to summarize, we can see that NTN has a clear evolution path. If we look to the left, pre-3GPP standardization, we can see that satellite networks and terrestrial networks were separated. We had expensive dual hardware and separate technologies. With the initial release, we have a technology integration, and we have benefits in terms of hardware. We have a unified hardware, and we can also already switch between networks. Then in the further release, we have performance enhancements. Some network elements will be deployed in the satellite, as Volker outlined. And we have a better alignment and improved mobility. And the target then later is, of course, to have a single network which is seamlessly interworking between the technologies. So for the user or device, it really doesn't matter. There will be a smooth operation between these two technologies. So there is clearly this kind of future vision to have then, let's say, a single network structure which can serve then the applications in a seamless way. If we look at what's happening today and at the market, there is already a lot of positive resonance. We have basically the ecosystem adopting already and embracing 3GPP-based satellite communication. So so there are already, here's a prize for this new approach in 2023 already. And as Telit Cinterion, of course, we are engaged already for quite some time as also being a member of the 3GPP standardization. So we have an active role there. We have strong partnerships within the ecosystem, and are also, of course, engaged in forward-looking projects. One would be, for example, the 6G NTN project. And finally, there is already a product. So with the ME910G1, there is a product available where satellite communications, 3GPP based, is accessible for IoT applications. So this concludes the presentation. We have, let's say, an overview here. If you are interested in learning more or trying, wanting to explore this technology, please give us feedback. We are also happy to have a second part of this presentation, which is maybe a little bit more doing a deep dive here. So feel free to contact us, and if there are further questions, we are happy to support you in exploring NTN technology.
Thank you so much, Florian and Volker. Audience, real quick before we wrap up, I am going to drop a poll on your screen here. If you would like to have one of our experts contact you directly, please just respond here on the poll, and we will be sure to have somebody reach out to you. Florian, Volker, thank you so much for your time today, and thank you really everybody who joined us.
Thank you.
Thank you.
Yep, have a good one.